Good morning, everyone. Welcome to our tutorial of knowledge-augmented methods for natural language processing. I'm Chen Guangzhu, Principal Research Manager from Microsoft Cognitive Services Research. Together with me for this tutorial are Yichong Xu, Senior Researcher from Microsoft Cognitive Services Research, Xiang Ren, Assistant Professor from Department of Computer Science at University of Southern California, Bia Yuchen Ling, Young Investigator from Allen Institute for AI, Meng Jiang, Assistant Professor from Department of Computer Science and Engineering at University of Notre Dame, and Wen Haoyu, PhD candidate from Department of Computer Science and Engineering at the University of Notre Dame. Besides me, all the other 5 presenters will be remotely joining by Zoom. First is a disclaimer. This tutorial reflects our own opinions, not that of our affiliations. And to access the mentioned models and datasets, please go to the corresponding websites to refer to their corresponding licensing information. And although we will be talking about a lot of models and datasets, we are not promoting any of these. And to better introduce these progress, we have borrowed some slides and figures from prospective published papers. And finally, this tutorial is by no means exhaustive, although we've tried our best to include relevant materials for you. And here to access the tutorial materials, you can go to the Wisdom official website for the tutorial, and also visit our website on GitHub for this tutorial. And here are the QR code if you want to access it. Okay. This tutorial in general is about how to fuse knowledge and common sense into natural language processing. And under this general concept, we will talk about how to integrate knowledge into natural language understanding, or NLU, including natural language inference, sentence classification, sequence labeling, etc., like namely all those discriminative tasks. And second is how to integrate knowledge into natural language generation, or NLG, including text summarization, dialogue response generation, story generation, etc., namely the generation tasks. And finally, the common sense reasoning, including common sense Q&A and common sense generation. Here is the schedule of this tutorial. I'm talking about the first part of motivation and introduction of knowledge in NLP. And then my colleague Yichong will introduce how to integrate knowledge into NLU, followed by Yuchen Ling and Xiang Ren about common sense knowledge and reasoning for NLP. And then there is a coffee break from 10 to 10:30. Then there will be a continuation of the third part. The fourth part is about knowledge in natural language generation by Wen Haoyu and Meng Jiang. Lastly, there will be a summary and a future direction discussion by Meng Jiang and Xiang Ren. Okay. Okay, so let's get into the tutorial. If we look at the recent development of natural language processing, we can notice a very clear trend of developing larger and larger models. And these models have become so huge that even for large companies, very few of them can afford the training cost. And if you say, okay, the pre-training is too costly, I won't do it, I will just fine-tune the pre-trained models, just like BERT. However, that has become impossible for a majority of researchers and practitioners. For instance, if it is estimated that if you want to fine-tune GPT-3 model on your data set, no matter how small it is, say just one pair of X and Y, you need at least 96 V100 GPUs to run that, which is out of budget for a lot of people, right? On one hand, we notice that there's the performance of these models are generally getting better when the models are larger. But does model size solve everything? If we further increase this GPT-3 ChatGPT models 10 times, 100 times, or even 1,000 times larger, will they achieve human level intelligence, just like talking to each other, just like humans? Based on our experience and also the research results from the community, the answer is unfortunately probably no. Even for the latest models, we can still note that it will make some very simple errors that humans won't make. And it is hard to explain why they make the errors. So there's still a gap between the current state and the human level intelligence. Then the question arises, why are we still doing it? Why are we still endlessly increasing the model size? To answer that question, I would like to draw an analogy where a man just lost his key in the park at night, and then he started to look for his key. But instead of looking for the key in the whole park, he just focused on a very small circular area illuminated by a lamppost. After an hour, he found nothing. And then one of his friends came and asked, why do you just search for a key in this small area? The man answered, because this is the only place I can see anything. So if we consider the human intelligence as the key we want to find, then definitely this small circular area represents what we can do. We can invest millions of dollars to develop larger models, get better infrastructure, etc., developing more, using more GPUs. But that doesn't necessarily lead us to our final goal. To reach the human level intelligence, we definitely need some other alternatives in addition to what we have right now. And just increasing the model size may not probably lead us there. So in this tutorial, we want to propose such an alternative, which is integration of external knowledge. Knowledge is not a novel concept in natural language processing. If you look at the central concept in NLP, namely the language model or LM, it basically learns how to express as naturally as humans do. After being pre-trained on millions and billions of human written text, it is not hard for a language model to understand that the sentence, I go school to want, is an ungrammatic sentence, while I want to go to school is correct one. However, knowing how to express, it's just one part of human language capability. The other part is what to express. And that's where knowledge kicks in. For instance, to answer the question, where is the painting Mona Lisa? The language model tells us we should start the answer with 3 words, it is in. But what to feel after in depends on some external information that's not present in the question. As humans, we know Mona Lisa is a painting. It is in a museum called Louvre in Paris, France. So the correct answer should be, it is in Louvre, Paris. While some people may argue that a language model can already have a lot of knowledge, we argue that it is highly inefficient. For instance, it may take tens of sentences, including Mona Lisa is in Louvre, Paris, for the language model to implicitly memorize this piece of information. But in comparison, if we use, say, a knowledge graph, we can use several nodes and relation edges to precisely represent exactly the same information. So this shows that representing knowledge in this way, like as an external source, is highly efficient. More than that, because knowledge sources can be constantly updated, like Wikipedia. Every day, thousands of people are updating it with the latest information. And this information can be understood by human. We can easily see, okay, this piece is incorrect, let's correct it. But for models, after it is being pre-trained, it is fixed. Or you can take the endeavor to endlessly continue pre-training or just restart the pre-training of the model using the latest information. And here, when we talk about knowledge sources in this talk, we categorize it into 2 general kinds. First is structured knowledge. Representative examples include knowledge graph, which I think most people know. That is a meta representation of knowledge, common sense, entities, relations, and etc. And also we will mention dictionary. Dictionary is actually a structured source of knowledge. You can consider it as a database where the key is the words and phrases, and the values are the explanations. And the good thing about dictionary is that it is, no matter how rare the word is, you will get an explanation for that entry. So it is different from, let's say, the long tail distribution in the general text. The second category is the unstructured knowledge, including Webley data, or generally unstructured text data, like Wikipedia text, documents, emails, etc. And also large language models, which stores the knowledge in an implicit way, like you can directly invoke the GPT models to get the result, or ChatGPT. So in general, we argue that knowledge is any external information absent from the input, but helpful for generating the output. So any information falling into this category will be covered in this tutorial. So now we know it is important to integrate external knowledge into NLP, but it is always easier said than done. So here, after summarizing or surveying the existing methods in this field, we can see that although there are many different kinds, in general, there are 3 steps to integrate knowledge into language models. First is grounding language into related knowledge. And then we need to represent that knowledge in certain ways. And finally, to fuse that representation into a language model. Now let's look at them one by one. First step is grounding language into related knowledge. For instance, given an input, say an input question, we want to answer it. Definitely, we don't need all the pieces of information from all the knowledge sources. That would be too much. Instead, we only need the related one to this input. So this step of finding the related knowledge to the input is called grounding. And this step can be done by methods as easy as string matching, or more advanced methods like NER, entity linking, information retrieval, etc., depending on the format of the external knowledge. So the key task of this step, grounding, is identify concepts and relations related to the input in the knowledge sources. Secondly, we need to represent the knowledge in certain ways to be understood by the downstream models, the language models. And in general, there are 2 ways. First is in textual format. The other is in embedding format. If we want it to be represented in text, we can say, for example, using the concept names, the canonical names of the entity from certain knowledge graphs or dictionary, etc. Or if you want more details, then we can resort to dictionaries to get the concrete description of the concepts. We can also use deep learning to represent the knowledge in vectors or embeddings. So here's an example. In knowledge graph, if we want to get the information for related concepts, we can just get the subgraph within several hops of the central entity, and then use graphic neural network or GNN to compute embeddings. So then the information for every node will be represented in a numerical vector. Now, the final step of integrating knowledge into language model is to fuse that knowledge representation into the LM. And how to do this step highly depends on how we represent it. If we represent it, the knowledge into text, then we can directly concatenate these textual information, the concept names, descriptions, etc., into the input information and directly just feed that into the language model. And this has the benefit of we don't need to modify the language model in any way. We just modify the text input. If we represent it into embeddings, then we can append or add that conceptual embedding into the word embeddings. For example, if the input is the pen is on the desk, we'll find that the pen is an entity we found in the knowledge graph, and we get this GNN embeddings, and then we can append or add that to the original word embedding of pen. Or a more advanced way is attention. So attention mechanism is the way of dynamically assigning weights to different pieces of information, depending on the current status of the computation. And here, no matter how you represent, what embeddings you represent the external knowledge, there will be several vectors. And then in the language model, say, because transformer is very popular, say it's transformer, then in each layer of transformer, we can insert a external attention layer where it computes the external attention, basically assigning different weights to this black and red, and then linearly combine them. So that will absorb information from external knowledge based on the current needs. And finally, this knowledge is fused into the language model process. So to recap here for the first part, integrating external knowledge into language model is very necessary. It may lead us to the human level intelligence. And how to do that, we summarize it into 3 steps: the grounding, the representation, and fusion. Okay, so that's the first part. And next, my colleague Yichong Xu will talk about how to fuse knowledge into natural language understanding. Thank you.
I'm Yichong. So let's jump into the second part of the tutorial. So I'm going to introduce how we use knowledge-augmented methods for natural language understanding problems. Yeah, I'm Yichong from the same group as Chen Guang. Yeah, so what is natural language understanding? So in natural language understanding, the task is to make some predictions about the properties of words, phrases, sentences, or paragraphs based on the input text. For example, I have 3 example tasks here. Like, for example, text classification. The goal is to classify the text into several categories. For example, sentiment analysis, that we want to classify like positive attitudes towards negative attitudes. Also, like the second example here is question answering. Like we want to answer some question based on our knowledge. For example, when did Star Trek go off the air? If you look it up, it's like sometime in 1969. And so we also have language inference, where like we have 2 sentences and we want to find some relation between them. Here, basically, we want to classify it into 3 classes, whether the first one entails the second one, the first one contradicts the second one, or they are like, it doesn't necessarily indicate each other. So like, for example, at the other end of Pennsylvania Avenue, blah, blah, blah. This one like kind of entails the second one, like people formed a line at the end of Pennsylvania Avenue. So, well, a lot of language understanding just requires some like semantic understandings of the sentences. There are some natural language understanding problems that does require some external knowledge to answer, rather than like just the knowledge within the sentence themselves. So, for example, we have fact verification, where we want to verify whether it's the fact is true or not. Like 2016 Tour de France has a total of 198 musicians. Whether this is true or not, like for regular people, he probably wants to look it up on either Wikipedia or maybe Google search to find the correct answer. The same applies for our previous question answering example. The Star Trek, like, it's not probably common sense knowledge of anyone else, like we also have slot filling or knowledge graph completion problems. Like if I ask that Kepulauan Sula is in which country? It's in Indonesia, but it's kind of a rare knowledge. And we also have entity linking. The task is to actually link the entity mentions within a sentence to the corresponding Wikipedia page. For example, the sentence here mentioned Vancouver Millionaires. It's a sports team, I think. Sports team based in Vancouver, and then since we want to link them into Wikipedia, we need to have the knowledge within Wikipedia to differentiate between different entities with the same name. So the tutorial here is based on several relevant literature reviews. I'll just paste them here. We also borrow some ideas from these literature reviews. The first one is like a survey of knowledge-intensive NLP methods. And the second and third one is mostly for like knowledge-enhanced pre-trained language models, language model pre-training. So like they also contain some good summary of relevant literatures. So this talk is divided into 3 parts. Firstly, we will talk in more detail about what tasks and benchmarks we care about for knowledge-rich NLU. And I will kind of follow Chen Guang's previous introduction to introduce the framework. We will also talk about the knowledge sources that we can integrate in NLU. This include general domain knowledge, domain-specific knowledge, and also common sense knowledge. And for integrating the knowledge into language models, we'll divide into 3 parts in more detail to talk about how we ground the knowledge, how we represent the knowledge, and how we fuse the knowledge into language models. And after that, we'll talk about some representative papers. So there are many tasks within NLU that requires external knowledge. For example, there's question answering that we covered, mentioned briefly previously. For example, open domain QA is that some questions that require some external knowledge, like in Wikipedia or web search to answer. Representative dataset is natural questions. It's a corpus of real questions issued to the Google search engine, and then like about general word knowledge. And we also have common sense question answering is that questions that require some common sense knowledge that are present in our brains, but not necessarily present in the language models. For example, a representative example is common sense QA. It's a multiple choice question answering data set that requires different types of common sense knowledge to predict the correct answers. So like what do all humans want to experience in their own homes? You probably don't want to experience laying eggs or like work hard. Is probably you want to feel comfortable. And there are some tasks based on knowledge graphs that are very relevant for a lot of applications. For example, we have entity linking. So the task is to link entity mentions in sentence to entities either in a KG or in a let's say Wikipedia. Representative dataset is this WNED wiki. It's a dataset automatically created by sampling documents from the 2013 Wikipedia dump and balancing the difficulty of linking each mention using a baseline as a proxy. And we have slot filling or link prediction, that is predict the tail entity given the source and relation. This is mostly, we have wiki database link prediction. The Llama Pro will naturally just transform such links into sentences and then for a language model to answer. And we also have knowledge-based QA. So this is based on, the goal here is to answer a question based on the knowledge base. For example, web questions is a question answering data set using Freebase as the knowledge base to construct questions, like based on the knowledge relation Bachelor of Arts, Barack Obama, Bachelor of Arts degrees is Bachelor of Arts and Juris Doctor. We can construct the following question: what degrees did Barack Obama get? There are 2 answers to this question. And more broadly, we have also more varied tasks like fact verification. This is increasingly important given the recent events like COVID, like ChatGPT. This is getting very important. The goal is to verify a given name from the public knowledge. Representative dataset is Fever. It's a large dataset for claim veracity that requires retrieving sentence level evidence to support if a claim is supported or refuted. We also have dialogue response generation. The goal here is to generalize response using the given knowledge, using some word knowledge. The representative dataset is Wizard of Wikipedia. It's a large dataset of conversation grounded with knowledge retrieved from Wikipedia. We also have common sense tasks. This will be covering our third part, like, for example, coreference resolution or next sentence prediction. They also require some common sense knowledge. So next I will talk about knowledge sources that we want to retrieve from in NLU. So we have the task, like where we want to retrieve knowledge from. We first have general knowledge sources, that is like everything in the world. The most prevalent source is arguably just the Wikipedia. It's one of the most prevalent sources, providing massive amount of encyclopedic knowledge, including biography of a person like Joseph Biden. Another such source is Wikipedia. It's a structured knowledge graph, which is a factual knowledge base aiming at uncovering graph structures of entities and converting them into structured database. So for example, we have Joe Biden has the occupation of politician. Joe Biden has a position held as the president of the United States. And we also have Wiktionary. It's a semi-structured dictionary, like where every word has one or several definitions. So it can be useful to understand keywords and entities in the given sentence. So for example, United States of America is a country in North America stretching from the Atlantic to the Pacific Ocean, blah, 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 things like that. In addition to Wikipedia-based knowledge sources, we also have other general sources of knowledge, like Freebase is also a large collaborated knowledge base based on data composed mainly by its community members. And similarly, we also have DBpedia and Yago. They are both like a knowledge source, like based on crowdsourcing efforts. WordNet, on the other hand, is something a little bit related to Wiktionary, but it's more organized. It's a large lexical database of English. The nouns, verbs, and adjectives and adverbs are like grouped into sets of cognitive synonyms called synsets, and each representing a distinct concept, and then we represent relations between the synsets by the edges. And we can also obtain general knowledge sources from language models like GPT-3 or ChatGPT. Is an autoregressive language model. GPT-3 is an autoregressive language model released in 2020 that uses deep learning to produce human-like text. And we can also use that as a source of knowledge to that better extract knowledge. We can, in addition to those general domain knowledge, we have domain-specific knowledge bases. For example, for the biomedical domain, we have UMLS, the Unified Medical Language System. Is a compendium of many controlled vocabularies in the biomedical sciences. You can think of that as a dictionary for biomedical science. And it provides a mapping structure among these vocabularies and does allow one to translate among the various terminology systems. It can also be viewed as a comprehensive ontology of biomedical concepts. And A-Miner or RNet-Miner is a free online sources used to index, search, and mine big scientific data. So it's like a knowledge graph or for scientific concepts and such data. We also have common sense knowledge. Here we introduce two types of common sense knowledge. One is general common sense knowledge, like open mind, common sense, ConceptNet, Trans-OMCS, common sense knowledge graph, or CSKG. They are all focusing on the general side of like word common sense knowledge. So here, like OMCS, the open mind common sense, here is a large common sense knowledge corpus from the contribution of many thousands of people across the web. And the ConceptNet is based on this corpus. They construct a knowledge graph that extract the knowledge as properties. For example, like apple is a fruit, and is a relation. Apple and fruit are both entities or concepts in the ConceptNet. And trans-OMCS and CSKG are both can be sort of extensions of ConceptNet, but with better coverage and potentially higher quality. And on the right side, we have also specific aspects of common sense, like the atomic. The two varieties of the atomic both focus on the human interactions that like the consequence of our everyday actions. And ASER is focusing on eventuality, and ARC is something more focused on the science or like elementary science aspect of knowledge. And next we can have we want to study about how we integrate knowledge given the task and given the knowledge source. Well, that of course depend on what kind of knowledge we have and what the task we want to solve. But we generally here we give a general framework. Given the text or the task we are solving, we want to have some knowledge grounding into a given knowledge source. The knowledge source is represented by some certain knowledge representation. And then lastly, once we have the knowledge presentation and the corresponding text, we want to fuse them together into a language model, which on the other hand gives a prediction for the given task. So how do we do the entity knowledge grounding problem? So this depends on what kind of knowledge we have. But for example, if we are having a knowledge graph as the knowledge source, we usually use entity linking method. Here, the goal is to link the text into entities in the knowledge base. People have used different kind of methods to link those entities, and sometimes just string match is enough. Like if we just have a moderately sized knowledge base, we just use string match between the text and the knowledge base. And sometimes people use entity linking toolkits, like Ernie use a toolkit called TagMe for entity linking. And if we are using Wikipedia or Wikidata, the hyperlinks within Wikipedia is a good signal for linking entities. For example, Entity as Experts uses such hyperlinks for entity linking. If we are using unstructured text like Wikipedia as the knowledge source, then we want to have some retrieval method based on the input query, and then we want to match it with some, say, documents or paragraphs using some retrieval-based methods. For example, DRQA is one of the first works in open domain QA, and they use sparse feature retrieval like TF-IDF to retrieve the paragraphs from Wikipedia. And we can also train a neural retriever that that embeds all the documents and questions as embeddings. It's called dense passage retrieval, or DPR, proposed in 2020. It's also a widely used method. And this is like we train a retriever when we have supervised data. But if we do not have supervised data, we can also use a fixed retriever for dense text chunk retrieval. Basically, for example, we can just encode everything in BERT and then use that embedding as the embedding for retrieval. For example, Retro use such methods. And we can also have like hybrid method, like we combine the retrieval result of sparse retrieval and dense retrieval, like it's done in K-Former. It's a 2022 paper. And after we retrieve the information, how we can represent the knowledge. For knowledge graph, it's naturally just entity embeddings. There are like pre-existing methods to embed knowledge, embed entities in knowledge graphs. For example, Ernie use trans-E to incorporate trained entity embeddings. And entity experts, they learn the entity embeddings through a series of different losses based on the entity embeddings. And we can also have contextual embeddings. For example, in Kepler, they use a Roberta to embed the description of entity as the embedding of the corresponding entity. So if we are using passages, then we are looking at passage embeddings. And for example, DPR is using BERT to encode every passage as a vector. And another way is, like, for example, in CoBERT, the idea is to encode every word as a contextual vector for retrieval. And we can have, and for knowledge fusion, we can have different kinds of methods. We divide them into several parts. One is pre-fusion method, where we fuse the knowledge into pre-training. The idea is that we add knowledge-related loss in pre-training. For example, Kepler, they integrate entity embedding losses like trans-E. And Erica, they use contrastive learning on the entities and relations for given freeform text. And we can pre-train the MLM loss on the corpus or KG to improve the understanding of some given knowledge. For example, the KELM linearizes the KG into natural sentences. A very important popular method is salient span masking, proposed in the Rion paper. The idea is to mask entities and mask the entities instead of mask random words, and let the model to predict the entities so that the model gets better understanding of the entity. And in ORQA, they replace entities with negative examples and try to detect those replacing examples. And we also have post-fusion method, where we do not want to change our language model, but we only want to change them during fine-tuning. For example, in KEER, they append knowledge as the additional text and just use that as additional knowledge for fine-tuning for specific tasks. In Yarner, a paper in 2020, they train the entity linking problem as a generation task directly. So from the entity mention directly generate the corresponding Wikipedia title. And in K-Former, they modify the feed-forward matrix to incorporate the additional knowledge. And we can also have a hybrid method that where we fuse in both pre-training and fine-tuning. For example, Rion uses retrieve passages to help predict entities in both the MLM pre-training as well as help the QA in fine-tuning process. The ERNIE also similarly, they retrieve entity embeddings from knowledge graphs and incorporate into model for both language modeling as well as the downstream tasks. And the Jackie, a little bit differently, they use GNN to process a part of the KG so that the knowledge graph is directly feeding to the language model, and they fuse the representation into the middle hidden layers. And they do this both for language modeling as well as for question answering. Okay, yeah, that's an overview of the representative methods. I will jump into some representative papers. Yeah, depending on your time, maybe I don't have time to cover all this. I will pick some representative papers. We have entity linking based methods. Basically, it's papers focusing on using either some kind of structured or semi-structured knowledge, like knowledge graph or dictionary. We also have retrieval-based method that we use free-form text. Mainly it's Wikipedia, but it could be something else to retrieve from as the additional knowledge. So let's jump into the first part. The ERNIE, which stands for Enhanced Language Representation with Informative Entities, is a paper that incorporates entity embeddings into language model. The idea is that we compute the trans-E embeddings from Wikipedia, and they use TechMe to link the text into entities, and they add entity embeddings to the attention in transformers. On the right, we have the model architecture. So in addition to the traditional token inputs as in BERT, we also have an entity embedding input, like the Bob Dylan here and Blowing the Wind is a song. And so we extract the trans-E embeddings of the two entities as some input into the model. And the multi-head attention is done both on the token inputs as well as on the entity inputs. They are done respectively. And then it combines the entity representation with the token embedding representations in a layer called information fusion, I think, and where the two types of representation are combined by a projection matrix. It also defines some specific pre-training laws and fine-tuning methods for integrating the entities. For example, entity denying is to let the model predict a mask or replace entity. In practice, they replace 5% of the entities and 15 of the mask 15 of the entities. And in fine-tuning, they sort of mark the entity mentions with special tokens, like here ENT or head or tail, here to give the model extra information to predict for the given task. They initialize from birth and continue to use their method to pre-train on Wikipedia. And they have improved performance on knowledge-intensive tasks like entity typing, relation classification. They also got improvement on the GLUE, like general domain NLU results. Second one here we have here, it's our group's paper. The idea is to augment self-attention with external attention. We do not change the language model architecture to just incorporate additional knowledge. The knowledge is from 3 different sources. One is from knowledge graph. Here is for common sense reasoning, so it's for the knowledge graph is ConceptNet. We also use definitions from Wiktionary, and we also propose a new retrieval method called retrieval from training data that retrieves similar questions, for example, for question answering, to augment the input. We use string match to find entities. For example, for a given question, for example, this is from Common Sense QA, what do people do while playing guitar, singing? And we can find the corresponding entity, like playing guitar and singing, and there has a relation, like playing guitar is a sub-event of singing. And we can find the corresponding definitions of guitar and singing from Wiktionary. We can also retrieve similar questions from label training data. For example, here we can find a man is seen what while playing the guitar, singing. This kind of quite related to the given question. So combining all the knowledge through the self-attention process creates some external attention between the input question and additional under general knowledge. The KM method achieves the human parity result on the Common Sense QA benchmark. As you can see, adding KM method can improve the result of electrons from 81.3 to 88.7, and using the best models and endeavoring gets it to a very high depth accuracy, which in turn leads to the human performance on the Common Sense QA benchmark. And I will briefly talk about this entity as expert method. Here is the idea is that instead of using like ERNIE, we use trans-E, like fixed entity embeddings. Instead we learn some entity embeddings to help language model. So for each entity embedding, we compute a pseudo embedding from the first and last token of the embedding tokens, like the origin of the species. This is a book. We compute the first and last tokens, then concatenate them, and we find the k nearest neighbors of the pseudo embedding here from entity memory that we pre-compute and learn, and use that for helping language modeling. So they train on Wikipedia with MLM and entity linking. The goal is to predict the mask words as well as link the entities into things in our entity memory. The hyperlinks in Wiki provides the entity linking, and the pseudo embeddings, we set them to be close to the true embedding. And then in prediction, the model just try to predict an entity by generating a pseudo embedding from the last layer and find the closest one in the memory. The entity as expert or EAE, they achieve good results on llama probing as well as open domain question answering that's focusing on entity prediction. The first one is sort of focus on extracting knowledge from knowledge graph. And here we have another paper on like using dictionary in BERT for training. Here the idea is to add definitions of rare words to help the NLU process. Here they have tasks designed to help models to use the definitions to help mass language modeling, as well as language subsequent and language understanding tasks. For example, here the first task is mass language modeling, and the second one, the task aims to have maximize the mutual information between the definition, the source word and the definition word. And the third task is definition discrimination, where sometimes there can be wrong definitions, like irrelevant definitions appended, and the model needs to differentiate whether this definition is relevant or not. BERT helps general and domain adaptation on NLU tasks, especially when they are rare words. It can boost the performance a lot. So now we have second part, we have retrieval-based method. Firstly, this is a very classical paper on like dense passage retrieval for open domain question answering. So given the question, we want to retrieve the relevant passages to answer the question from Wikipedia. And so we use a BERT model to encode both the question and passages. We train the BERT to get similar representation for Q, the question, and positive passage. And this is contrastive learning. We use to try to increase the probability of choosing the positive passage against several negative passages, basically random passages. For a new question, we can use fast nearest neighbor search to find the closest passages. So the DPR obtains very favorable result compared to BM25, a classical sparse retrieval method. And sometimes combining them can obtain better results. And like both, they obtain good accuracy, both in the retrieval accuracy, basically when we retrieve some passage with the correct answer, as well as the end-to-end accuracy, basically the end-to-end exact match results of question answering problems. The REALM is another representative paper here. It stands for Retrieval-Augmented Language Model Pre-training. So it's the idea is to apply dense retrieval for language model pre-training. Idea is similar to DPR, but it's applied for language modeling. We retrieve relevant passages to help the MLM in pre-training, as well as downstream tasks in fine-tuning. They jointly train the retriever and the language model so that they can improve together. It also achieves very impressive results compared to previous methods like ERQA and ORQA based on dense retrieval methods for open domain question answering tasks. So previously we looked at retrieval from Wikipedia. So let's look at retrieval from something else. So RENA stands for the paper is like training data is more valuable than you think. It stands for retrieval from the training data. The idea is that for a given task, we retrieve similar examples from the training data itself. The training data is arguably the most similar text in distribution to the given task. And the RENA builds the training data as an input and output key value index. And so given the new input, they retrieve the similar inputs and use the output as the knowledge. It can be applied for not only NLU, but also NLG tasks like summarization or language modeling, as well as question answering like NLU tasks. We can build the index like basically key value pairs from the document to the summary as in summarization. For the first chunk mapping to the next chunk for language modeling. And for question answering, it is just based on the same construction, like the Q&A maps to the same Q&A. For the given question, given query, like the document and context or like question and candidate for question answering, we retrieve based on the key and get back the corresponding value. The idea is that after we retrieve them, we get the summaries of similar documents for summarization, get the next chunk of similar first chunks in language modeling, and get the golden question answer pairs for the given question and candidates. After we retrieve them, the knowledge is basically appended into the input and used for subsequent model training. It can be either a sequence-to-sequence model or an encoder model. The RENA method achieves impressive results on a series of different tasks, including summarization, question answering, machine translation, and language modeling. And lastly, we have replug. It's a very recent paper. Previously, we focused on like optimizing the language model. We have like external knowledge source, but they are like the language models are sort of small. So nowadays we are focusing on large language models and like ChatGPT, and then we cannot necessarily fine tune them. So how can we do retrieval in this case? So here's this paper called replug, which stands for Retrieval-Augmented Black Box Language Models. The idea is that we, given a text context, we use some offline retriever to retrieve some documents as the additional context, and then we prepend the document with the corresponding input or basically some questions, and then for each document we construct one input like document concatenated with the input, and then we can ensemble them based on different predictions. In this way, we do not need to train a retriever. We do not need to fine-tune the black box language model. We use that as a source for retrieval, and then they can already augment the language model's performance because it has additional context. And then if we want to train some part of it, remember that we can train the retriever. The reason that we want to train the retriever is that for large language models like ChatGPT or maybe GPT-3, they already have some knowledge. So the motivation is that maybe it just wants some like a long tail knowledge or some rare knowledge instead of very common, like common sense knowledge from the retriever. So to train the retriever, we can try to maximize the probability of the document that leads to the correct answer. Or like maybe next sentence in language modeling. So for test context, we retrieve the corresponding documents, and then we compute a retriever likelihood based on the retriever, and then we can compute the language model likelihood based on the document concatenated with the given query. This is we make it proportional to the language model probability prediction. And then we try to compute the KL divergence between these two, so that like helpful documents are given higher probability from the retriever. Replug gets very good performance on language modeling, MMU, LU, and open domain QA tasks. And thank you. That's it. Any questions are welcome before we jump to the next part.
So in this part of the overview, we will introduce how to incorporate common sense knowledge into neural language models. And Xiang is the assistant professor at the University of Southern California, and he was also my PhD advisor. And I just graduated. I'm a postdoc researcher at Iden Institute for AI. And due to some technical problem, I will play Xiang's recording for his brief introduction to this part. And then I will continue presenting the main content of this part of the overview. So it's just a second. Let me I think I should reshare my screen. Just a second. Yes, here it is.
So in recent years, we have been seeing AI models that making tremendous improvements over time, right? In particular, these fine-tuned pre-trained language models, such as BERT or Robota, has been the de facto standard for learning different natural language processing models for a variety of downstream applications. So these models sometimes have even show like superhuman performance on a lot of popular benchmarks, such as Squad and GRU. However, natural questions we'll be asking is like, does these models really suggest our natural language processing techniques nowadays have human level intelligence? So I want to show you a few examples in the following, just to give you a sense of why we think that this current model, even though they have achieved pretty good human performance on some benchmark data sets, are still far from having human level intelligence. Right, the first examples here is a English to Chinese translation. So there's two possible ways to understand the meaning of this input sentence, right? The input sentence here is the fruit flies like a banana, right? So the two ways we can see these sentences, one is we can truncate the sentence by like the and then fruit flies and then like and bananas, or we can understand in another way where we see is as the fruit flies like a banana, right? So if a machine which have a human level intelligence, they could possibly infer that the fruit are not able to actually fly. So then the second choice we're showing here is less plausible as a valid translation for the original sentence, right? So this means like even though both options are grammatically correct, but only one are aligned with our human common sense more. Right? If a system that are able to make such distinctions with enough common sense knowledge, then this is actually not a very difficult case for the machine. But still, we are seeing such mistakes being made in many of the examples in machine translation system. So next example here is a name entity recognition example, right? So the first sentence here shows like Yu Chen would travel to NYC for the ACL conference, where the system correctly identified Yu Chen here is a person, NYC is a location, and ACL is an organization. But with a very similar sentence, which only have one changes to the word from NYC to ZYC, the system start making silly mistakes, which puts this ZYC into an organization label. So this is kind of a likely happens for systems where they capture some popular syntactic patterns and have understanding on popular words like NYC, but these features, these such model learns are less likely to generalize to long tail vocabularies or phrase like ZYC. But a system with common sense will likely avoid making such a mistakes because they see in the phrase like travel to, they will likely just infer the word adjacent to it will be a location rather than an organization. So lastly, if you look at another example in the domain of visual question answering, so these images here is showing the person is actually likely taking a picture on a structure on the left-hand side. And the question is asking, what is the man holding in his hand, right? Among these possible answers like backpack, bag, camera, luggage, and strap. For human, it's likely to infer the person here is holding a camera rather than holding backpack or luggage, because in order to perform the action of taking a picture, likely the human needs to hold a camera. And this kind of common sense knowledge, if lacking in the current model, then the question here will be harder to address correctly. So generally speaking, what we care about here is what we call common sense reasoning. And this is usually refers to the skill of making proper assumptions about our daily life situations, or in other words, use the common sense knowledge about our world to make presumptions about everyday situations. And based on these examples, we want to argue that it is of vital importance to incorporate common sense knowledge to develop a more general and human level AI system, including the natural language processing models we talked about today. so that they can reason with common sense and thus think, talk, and act more like humans. So the natural language processing models we are talking mostly today are these neural large pre-trained language models, such as BERT, GPT-3, and BART or T5. So in the following content, my student Richard will introduce how we can incorporate common sense knowledge into this massive neural NLP model.
Okay, so that's Xiang's part, and I will continue the slides just a minute. Okay, so we were here. Yeah, so thanks for Xiang's brief intro. And hi, I will take it from here. So in the following part of this tutorial, we will first introduce the background of common sense reasoning and in NLP, the NLP context. And then we will introduce the methods of incorporating structured and unstructured knowledge to NLP models. And in both parts, we will mainly use the question answering task to showcase our methods. And finally, we will introduce a text generation benchmark for evaluating the common sense of natural language generation models, as well as a few knowledge augmentation methods towards it. So before we dive into the knowledge augmentation methods for neural LLMs, let's have a look at the common sense performance of the language models if we do not augment them with common sense knowledge. So let's look at the masked language models like BERT. So one of the most simple methods to analyze if such language models have common sense in these models is the llama probing. So by llama probing, we can see that if we mask the word here in the sentence, like birds usually can do what? And the prediction of bird are mostly correct, meaning that the bird without any additional knowledge augmentation already captures some common sense to some extent. However, if we ask tigers, like tigers usually have how many legs, and the answer are then surprisingly wrong and irrelevant. So this is to say that common sense knowledge inside these language models are still pretty limited. And it's quite similar to the autoregressive language models too. So it's different from BERT. So this kind of like autoregressive language models like GPT-2, and this is a coreference resolution examples where we need to infer which object the pronoun it refers to. So is it because the trophy is too big, or is it because suitcase is too big that they cannot fit? So using autoregressive language models, we can then infer this by replacing the pronoun it with two possible options, and then use the sentence probability to decide which one is the correct choice. So this method does not need any external common sense knowledge. However, the accuracy of this method is only like 63% of accuracy, while the random accuracy can already be 50. So it's quite limited if we do not augment language models with external common sense knowledge. So as for the encoder-decoder language models, which is also very popular, like T5 and BART, so we use unified QA model here, which is based on T5. And we can see that if a fine-tuned T5 model can generalize for common sense questions. So in this question, like what do you fill with ink to write notes on a piece of copy paper? The correct answer is A, like we use pen to do that. But the answers for from T5 model like unified QA, they will give wrong answers like pencil case or printer. It's because like printer are also related to filling with ink, and pencil is related to write something. But so they, if they do not have enough common sense knowledge, they cannot answer such common sense questions. So based on these findings, like we argue that knowledge augmentation for common sense reasoning in NLP, it is very important, and not only for achieving better performance on NLP tasks, but also for developing some more like transparent and interpretable and trustworthy NLP models. So to evaluate these methods of using common sense knowledge to solve NLP problems, there have been many benchmark datasets created in these years, and most of them can be converted to multiple choice QA settings. And one of the most popular data sets here is the Common Sense QA, where there are 5 answer options for a given question, like this one. And but the model is then asked to select the best option for answering the question. And this multiple choice QA setting is it's a closed environment for analyzing the common sense performance of language models. This is very limited because it doesn't match our realistic scenarios. So because in our applications, we may not have any predefined answer candidates as the choices for a question. So therefore, recently people propose like open-ended QA, where only a question is given as the input, and the model needs to use a corpus, a knowledge corpus, to output the multiple correct answers to it. So this is another challenge here, because not so many questions they have more than one correct answers. So we will need to retrieve all of them. So this is more closer to our realistic applications. And so we will also present a message to this kind of like open-ended common sense reasoning. And other than this natural language understanding applications, the common sense reasoning community now also focuses on the text generation tasks. So in the last section of this part of the tutorial, we will introduce a benchmark named CommonGen for assessing the generative common sense reasoning ability with constrained text generation task. So let's get started with the direction for incorporating structured common sense knowledge to solving reasoning problems. So by structured common sense knowledge, we usually mean like a knowledge graph structure, like Yicheng just mentioned. So in this kind of knowledge graph, we use each node to represent a concept, and edge between two nodes indicate a specific type of relation between two concepts. So for example, there is an edge from baking to oven. So that means the label here represents the relation used for. So this means we know like oven is used for baking. And the advantage of using such structured common sense knowledge is that they are easier to construct, and they are also easier to query, retrieve, and to be used in language models. And we aim to use common sense knowledge we may use some part of these knowledge graph structures to support interpretable reasoning of neural network-based NLP models. And so some people may also call this like a neurosymbolic approaches for common sense reasoning. And we, for example, to answer this question, where do adults usually use glue sticks? So if we want to justify the option office here, so then we will need to retrieve a subgraph from the concept net. Concept net is a very popularly used knowledge graph for common sense. Then we can retrieve a subgraph this concept net where the concepts mentioned in the question and also the option are connected with additional edges and additional nodes. Then we call this graph as a schema graph. So the motivation here is we can retrieve such schema graphs which are very relevant to the question and one particular option. Then we can use this additional common sense knowledge from knowledge graph to help us reason whether this option is a correct answer to the question. So we call this is interpretable common sense reasoning. And so CogNet was among the first methods in this knowledge-aware common sense reasoning methods. The general pipeline here for CogNet is like we need to recognize the concepts mentioned in the question and one particular option. Then we have a question concepts, which are maybe some phrases, some nouns mentioned in the question, and also some nouns mentioned in the answer option. Then we extract the concepts for the question and answer. Then we can find the paths that can connect each pair between the question concept and answer concept. Because these connected paths are likely to be very useful for our reasoning, and so we can tell whether this particular answer candidate is a correct answer or not. there can be a very large amount of such paths because the graph, the common sense knowledge graph itself is very large. And also the paths between two concepts can be also very large. So we need to control the size of the schema graph. And we also need to add some heuristic-based method to form the graph so that we can have a suitable size of the graph for future encoding. And so the final schema graph is then encoded by a graph network. And here we can use like graph attention network, like graph convolution network, and some other stuff. As long as we can encode this graph into a dense vector, then we can merge it with with the language encoder results, like using BERT or using other language model. We can get another dense vector from the text part of the question and answer. Then we can merge them together with the graph vector to use another multi-layer perceptron as the final layer to classify whether this answer candidate is a correct answer or not. Then we can learn to use this plausibility score to get the final choice for this question. Okay, so specifically in CACNet, how can we do this? Like the graph encoder, I mentioned that you can use a graph convolution network followed by a path with the WSDM network. So the graph convolution network here produces the initial representation of all the nodes, because you know the structure here, and you know, like if two nodes in this schema graph, if they are closely connected, then maybe they are more related. So their representation will be also related to each other. So that's why we use the graph convolution network to get the initial representation for these nodes. And then we know all the paths between a pair of question node and the answer node. Then how do we represent the information on each path? Here we propose to use LSTM to do that. So the LSTM here will take a sequence of triples as an input, and then we can generate the final hidden stage as the final representation for this path. But during this process, we need to consider that, we have so many different paths between a pair of concepts, and also we have many different pairs of question concept and the answer concept. So here we have to do some aggregation of them and to get the final graph vector. And also in this process, we will also merge the statement vector from the language model as part of the encoding process, so that we can also get the more information from both the symbolic knowledge graphs and also from the language space. So note that I mentioned that we have two levels of aggregation, the path level. So we have all for each, the first level is the pair level. So for each question and option, we may have maybe 5 question concepts and 3 answer concepts. Then in total, we have 15 pairs of them. So we need to do some aggregation. And for each pair, we may have maybe 5 paths. Then we also need to aggregate the paths. So in this case, we will need to propose like a 2-level attention mechanism to aggregate all this information. And also this attention network will be very useful for us to interpret the decision-making process. So for example, here we can see for this question, CACNet can predict the correct answer and the fountain pen, but the other methods cannot. So the benefit of knowledge augmentation here is that we can analyze the behavior of CACNet very easily in a transparent way, because we can use the attention score here. So we can see that in which particular pairs of concepts are more relevant to the decision-making process. Also, we can see that which particular paths are of higher utility score, such as they are the rationales for making the selection of this particular answer. And given this external common sense knowledge, the reasoning process can be more trustworthy. And the CACNet was also the best performing method the best performing method as its publication time compared to other methods that are also based on BERT. But CAGNet also has some issues, especially for the scalability issue here. Yeah, because there are a very large number of paths from the knowledge graph, and also the paths can be also very long. You may have a very long sequence of triples. This can lower the efficiency because the fact that LSTM must be executed in a sequential way. So can we do this better and more efficient? And to address this issue, we have a follow-up method named the MHGRN. So the MHGRN here, they want to enhance the efficiency of graph encoding stage by adding the support of multi-hop relational message passing. So the key motivation here is like the relational graphs can be modeled as a multi-hop message passing with a multi-layer graph attention network. So to give a more background on this, we will maybe have a small recap of the traditional relational graph convolution network. So here we can see that the final graph embedding from GCN, they are just the average of all the node embeddings inside this input graph. And in each layer, we update the representation of a node by aggregating the messages from past from its direct neighbors, like one-hop neighbors, which means that it is a single-hop message passing. And the different relation types here, because let's say we have maybe 40 different relation types in ConceptNet, then they need to have a 40 different weight matrix to represent each of the relation type. So it is simple and also easy to implement, but the power of representing a multi-relational graph is very limited because we can only do single hop encoding here. And in contrast, the advantage of CAGNet, as we mentioned before, is that we have an LSTM network. This LSTM can encode each path between two nodes. So it's more about like the reasoning process, reasoning chain here, and that you can use this LSTM to to represent the information flow along a longer sequence of edges very easily. But it's very it can be very slow if you have a long path here, and if your graph is more dense, then it is more slow. So the proposed MHGRN aims to combine both the benefits from both sides. It follows the multi-layer structure of the graph convolution network, and it also tries to get a multi-hop relations from the CAGNet idea. So you can see here, instead of using a single W matrix for representing a single hop behavior, single hop neighborhood, and the behavior here can be like we can have up to K matrix to represent the node features with a much larger view scope. So you can consider this MHGRN is more efficiently learned with if we use some low rank approximation here, the efficiency can be very much improved. And so this is a comparison here between MHGRN, CAGNet, and other methods in terms of their time and the space complexity. And we can also see that under both dense and sparse scenarios, MHGRN is more efficient than CAGNet, and performance is also very comparable and even better than CAGNet. And a more recent model, QAGN, it also relies on graph network. It's from I think it's from Stanford, and this idea is very interesting. So instead of merging the statement vector from BERT or from other language model at the end of the graph encoding, so they put the knowledge model, the language model results in the beginning of graph encoding. So the QAGN propose a special node here called context node. It is the purple node Z here. Also, there are two more special relations. The edges between the context node and the question node, the question concepts here, is the type called C to Q, like context to question. And then the edges between the context node Z here to the answer concepts, they are called C to A, the context to answer here. Then the node Z here represent the semantic features in the context of this question answering process. And it's initialized by a pre-trained language model. And this simple modification of graph structure and the graph encoding pipeline here enables like better attention-based reasoning and interpretability, because in the beginning of the graph encoding, they already know that your question and answer interactions, their attention mechanism in transformers. So we can clearly see that the reasoning process can be iteratively improved over time, like from the first layer to the last layer. And also, if we use a BFS here to search and iterate nodes, then we can get a very straightforward reasoning chains to explain all the model decisions here. So, and also there are, I think, two more follow-up work based on this architecture. It's called GRIS LM, or another, the other is called like GNNIS counter. And so here we can see the empirical results from the three models we introduced today, like TechNet, ImageGNN, and the QAGNN. They are all based on Roberta encoders here. And the QAGNN is significantly improves the performance, and we have to like skip the other follow-up work, which are also very exciting and important. Okay, so that's the part for incorporating structured knowledge of common sense to language models. So now we will go to like how we can incorporate unstructured common sense knowledge for open-ended common sense reasoning. So for this kind of like a structured common sense knowledge, we use the concept net, but the concept net, it has a lot of limitations. Like for like they can only support binary relations, like A is used for B, or A is usually found in B. So you only have for each fact stored in such knowledge graphs, you can only mention two concepts at a time. And also the quality, because it's from like human annotation, but some annotators, they may not have a very good quality responses here, and so that it can be very noisy and incomplete. So this remains like, why don't we use some sentence, just the original sentences like that are about common sense knowledge? So for example, this is called the generous KB. So this is a very large common sense knowledge corpus released by AI2. So we call this as a unstructured common sense knowledge base. And it can be directly used for open-ended question answering, especially because for this open-ended reasoning, we need to do retrieval a lot. So this corpus can help us to support multi-hop reasoning. So so before we introduce the method, so we can have a recap here. So the question is like, is
sorry, can I interrupt you for a second? Just to let you know, in 3 minutes, we're going to have the coffee break. Can you put that into your planning?
You were talking about the incorporating structured common sense knowledge for language models. And right now we can move on to incorporating unstructured common sense knowledge to NLP models. And as I mentioned, that there are some limitations for structured common sense knowledge graphs, the binary relation, and some incompleteness and noisy of the noise relations, the knowledge graph. And maybe we can consider how to use unstructured common sense knowledge bases to improve NLP and also to improve common sense reasoning. And here I can just show one question like we have been thinking about, like how is multiple choice QA. It's very useful in realistic applications. So when we query common sense knowledge in search engines and test AI models like chatbots with common sense questions, and we also we use robots to do some everyday tasks for us. And so, but in these application scenarios, users usually do not have any predefined answer candidates. So if we want to use common sense as a service for practical AI applications, models that are specifically designed for multiple choice common sense reasoning will be less useful, and it's very difficult for us to use them for real applications in production. And so we want to propose like a open-ended common sense reasoning. As we mentioned before, like the open-ended CSR only use questions itself as the input, and the output will be a ranked list of concepts that are acceptable answers to the input question. So this is possible if we have a very large test corpus of common sense facts, which contains the facts such as 1 and 2 here. Like the first one is carbon dioxide is the major greenhouse gas contributing to the global warming. And the second fact would be like trees remove carbon dioxide from the atmosphere. So combining this fact 1 and fact 2, we can answer the question better. Yeah, because these two facts together can tell us tree is one of the acceptable answer to this question. And we believe other useful combinations of these facts can also arrive at some other correct answers like renewable energy and solar battery and stuff. So therefore, our focus in this part will be how can we teach machines to reason in such a multi-hop retrieval way to answer open-ended common sense questions. And but this is a very challenging problem because like other like multi-hop questions like who voiced the dog in the TV show Family Guy, it is very clear for us to decompose these long questions into multiple sub-questions like the dog in the TV show and who voiced the dog. So there are some clear and explicit hints for acquiring the knowledge in knowledge bases like Wikidata and other like DPpedia and stuff. So for common sense question, it will be very difficult because let's say for this question, what can help a little bit global warming? It does not directly tells you how to decompose this question into like the sub question 1, like what contributes to global warming, and then what can removes the answer to sub question 1. So the first challenge will be like this is the latent and the implicit reasoning chains behind these common sense questions. And also the search space comparing to multiple choice QA, it will be very huge. Like you can consider all the acceptable answers here. The space can be very large. And also it has more dense links comparing to factoid questions. And so then we designed some like resources for using unstructured common sense knowledge for solving this kind of open-ended questions. So first of all, we have to have a corpus, a knowledge corpus, which here you can consider like WSKB from AI2. And this corpus, each element in this unstructured KB is a fact. And this fact, you can just think is a sentence of generic common sense knowledge. And each concept here will be a noun or a non-chunk or non-phrase like, that are mentioned in this sentence. And then we have a very large vocabulary of all the concepts. And this concept will be used as the vocabulary will be the candidates for answering the questions of open-ended common sense reasoning. And so here we model this unstructured common sense knowledge basis as a hypergraph. So we can consider you have a lot of sentences here, right? And each sentence you may mention multiple concepts. So we can consider this is a hypergraph here means like you, for each hyper edge, you can connect multiple concepts at a time. So in this formulation, it will be easier for us to connect different facts by if they have if they share some common concepts that are mentioned these two facts, then we consider these two facts are linked to each other. Then based on this formulation of hypergraph, then we need to do some dense encoding. So this dense encoding, we can use some existing language model like BERT. So we can get their vector to represent each sentence, each fact in this corpus. And we can also build a sparse matrix about the concept to fact. So because each fact, they may link to multiple concepts which are mentioned in this sentence. So this is a very sparse matrix, and the size will be the size of the vocabulary times the size of the total number of the facts in this corpus. And also we can have a fact-to-fact links. So like I said before, we can consider the hyper edges between two facts. then when there are when the two facts share like more than two common concepts, and also they are semantically related to each other, then we will create a link between the two facts. So this will help us more efficiently find the related facts between multi-hop retrieval. And then we will also use a weighted set of facts as a sparse vector to, as we use sparse vector to represent like a set of facts. So because when you have some non-zero value for each fact in the corpus, then we will consider, oh, this fact may be is considered as a element in this fact set. So given all these fundamentals and notations here, we are going to introduce the overall workflow for the proposed Dr. Fact flow. So given a question here, like what can help alleviate global warming, we first use BERT as a question encoder to get its dense representation. So a shared query embedding and multiple hop-wise embedding. So this is for because for each query step, you may have a different attention for this question. Maybe for the first few hops, you may look at the global warming. Then the second or the third hop, you are looking at working on the alleviate part. So this is why we propose to have a multiple hop-wise embedding of the question. And we also construct the initial facts by using the fact index, the dense index, and also the sparse matrix. Then to get the initial facts here, we call this F0. So F0 is a sparse vector, and the non-zero element in this sparse vector will be the facts associated with the question. So the initial facts are represented here. And the fact that we define these initial facts are like they must contain at least one concept that are mentioned in the question, and also they are semantically relevant to the question. So these are the definition of the initial facts. And when we have the initial facts, then we can do this multi-hop retrieval by iteratively using the hop-wise query embedding and also the previous hops facts as an input. So we have two parts of input. The first is the hop-wise query embedding, and also the fact set from the previous hop. Then we can continue doing this for multiple hops and arrive at the final hop, and we will use another re-ranker here to get the final rank list of the concept as the answer. So in total, we will have three components here. So you can consider this process as we are modeling the probability of a concept as the answer to the question Q. So C here is a concept. So PC given Q will be the first. We will have F0, the initial facts, and we continue doing this kind of fact following operation to get the second and third and final hops fact sets. And in the end, we will have a fact to concept module to help us find the final answer here. We can use a concept re-ranker, which is an optional module, but if you have this, you will have the performance will be much improved. And so specifically how we can design this fact follow operation, this is the hardest part, because like I mentioned, like if we only use a dense vector here, it will have some concept drift. So for the first hop, maybe it can provide the most relevant facts that are related to the question. But when you have multiple hops, it will be very likely that the second and third hop, the result is more and more far from the original question. So that's why we may need some like a sparse facts, a sparse matrix to help us control the concept drift phenomenon. So we will still first go with the dense index using the previous hops facts. Then we get their dense embedding, and we aggregate all these facts as a HT-1. And we also have our hop-wise query encoder, query embedding, and then we can just form a new query called ZT here. We learn to generate this new query embedding ZT to query the dense index again and to get their most relevant facts for the next hop. And in the meantime, we also use the sparse vector, sparse matrix to get what are the facts are linked to these given facts. So because if two facts they are linked, it means like they have their common concepts and also their semantics are very similar to each other. So they are more likely to be the next hop facts. So then we will have this, we merge this sparse results and a dense query result and sparse query result to get the sparse dense mixing to get the final FT for the next hop to use. And here we also have some technique called self-following, because if you don't have this self-following here, it means like we can consider some most important facts in the previous hop will be continually important in the next hop. So if we don't have this one, it will be very easy to have a very, very like nonsense facts in the next hop. So this is to ensure that the two hops are coherent with each other. So we found this is also very important. And so for some previous methods like Dr. Kate and other multi-hop reasoning, they will have to predefine hops you want to do reasoning. But with this self-following technique, you can define a very large T, and you only need one model to do all this multi-hop reasoning. So this is a comparison. Like for this open-ended question answering, you can use some retrieval methods like WSDM-23. You don't need to train this model. You just like use the index is our sparse features. And DPR is dense passage retrieval from I think it's from Meta, and they also can do this dense retrieval. So it's quite similar to our the dense part of our project. And for the Delta K, it's very similar to Dr. Fact. You can know that from the name. But their focus is how you can look at the entity co-occurrence, and they also work on the entity following. Because like for those factoid questions, like who was the dog in the TV Family Guy, is you have very clear like entity boundary, and also the links between these entities are very sparse. So for many, even for some popular entities like Donald Trump, if you consider it's knowledge graph, the links to these entities still very short. The number is small, so it's very sparse. So you can do this entity following. But in our case, we found the common concepts like water or global warming and some battery. So it's very common in the corpus. It can appear in many occurrence with other concepts. So this is why we propose fact following, because our number of facts is relatively smaller. The size is smaller, so it's easier to do this fact following. And the additional benefits of fact following is like you can keep all the original context from the previous hops to the next hop, instead of only using the entity embeddings, which do not have the whole context for reasoning in multi-hop fashion. And we to evaluate the methods, we also use some we create an open CSR dataset. It is created by some reusing some existing multiple choice dataset like ARC, OBQA, and QSC, but we provide some new additional human annotation to make it has multiple correct answers for each question. And we also define some new metric based on like a ranking work, and we use some metric here. But in short, our conclusion is like you can look at this the left-hand side. We can see the Dr. Fact is always outperforming all the other retrieval methods. And when you have a re-ranker here, so you're using the same concept re-ranker. This concept re-ranker is basically a multiple choice model. If we use this one, you can still see like there is a very large improvement for all the methods, but still Dr. Fact is the best model here. And if you look at different case, so if we only look at like the top 20 results, and or versus you look at the top 100 result, but from this curve we can also like verify the effectiveness of Dr. Fact is consistent. So we can skip this part, but it's about the efficiency here and if for some application study. But I want to show you this one. So this is a case study. So like what will separate iron filings from the sand. So if you use DPR, they will mainly working in the way like you look at the semantically values are similar to each other. But if you have a daughter fat, we will have some sparse filter, like the iron failings will be considered as one hint for us to query and retrieve the most relevant facts instead of only rely on the dense embeddings, which can cause concept drift here. And so the findings here, that's like OpenCSR is a novel setting for studying common sense reasoning and more realistic and challenging. And Dr. Fact is an effective and efficient method for this open-ended common sense reasoning. It has a differentiable fact following operation and it supports end-to-end training. And also it provides like state-of-the-art performance compared to other baselines. So that's how we incorporate unstructured common sense knowledge to common sense reasoning. And in the end, we want to introduce a benchmark and some relevant works for common sense knowledge, incorporate common sense knowledge for natural language generation. Because previously we were mainly talking about how we can do like answer a question answering. Most of them are like understanding problem. But for generation, it introduced some new challenges here. So Common Gen, what motivates our research here is like most of the current common sense reasoning tasks mainly focus on discriminative reasoning problems like common sense QA and SWOT dataset. So humans do not only use their common sense for understanding text, but also for generating sentences. So we just propose a data set called Common Gen. As we can see that an input here is a concept set, which is a collection of objects and actions. And for example, here is a dog, a frisbee, and the action catch and throw. So the desired output is a sentence that describes the everyday scenario in our daily life using as many given concepts as possible. So a simple example here would be a dog catches the frisbee when the boy throws it. So why this is problem so difficult? So first of all, it needs much relational common sense knowledge about the given concepts. But these relations are very latent and conversational. You need to have multiple pieces of let's say triples from knowledge graph to reason about this the relations behind these given concepts. And also you can see the data set covers many different types of knowledge, such as spatial knowledge, the properties of objects, and the human behaviors and temporal knowledge and others. And the second challenge here is the data set needs compositional generalization ability. So for example, in the training time, we can only see such examples about apple, bag, food, tree, pig, something, basket, and wash. But in the testing time, the model needs to deal with a more challenging example like this one. The model has never seen the concept appear in the training time, and the combinations of these two are also never seen in the training time. So here are some statistics of our dataset. And we need to note that the concept pairs in the test concept pairs are not showing the training before. So this is totally unseen. And the model thus needs to have this kind of conversational generalization ability so that they can reason and generate. And these are some performance of some previous generation models. And we also have a leaderboard, but it has the latest results. And we want to show you some case study here. So you can see for this given concept set is hand, sink, and wash and soap. So for all these machine models, their generation are not that don't make sense in real world, but our human annotators can provide more like feasible scenarios in our daily life. And also, when you have such a common gen model, you can use it to generate some, you can pick up some keywords from the questions and then generate some scenarios as additional context for question answering model. So it's also, although it's designed for testing the generative performance of common sense reasoning, it can also help the discriminative and understanding problems for common sense generation. This is a leaderboard, and we have more and more submissions. This is a very outdated picture, but for our leaderboard, you can see some companies and also some very famous institutions. They are working on this problem, and one of these methods is this one is very interesting. It's called KG bar. The bar is a model like T5, and they use some additional triples from knowledge graph to improve the generation ability of these language models. So it's also based on using structured common sense knowledge to improve the generation ability. And also there are some KGR. So this is a typical method. They try to retrieve some scenarios from their very large corpus and then use them as some starting point and as the prototype for continual editing based on those retrieved examples. So this is also a powerful model. You can consider this as incorporating some unstructured knowledge here. And this is a recent work called Imagine and Verbalize. It's quite similar to the previous one, but it has a structured and unstructured data together. So it's a mixture of the knowledge graph and also their captions, but they all convert them into scene graphs and then do this retrieval and generation. It's also very powerful. So in the end, I want to give a review here. So we introduced the background of common sense reasoning in NLP, and we introduced some methods like HackNet, ImageGen, and QAGen. So they can all retrieve some knowledge. So they can retrieve some subgraphs from a larger knowledge graph as additional structures for the language models to improve the reasoning ability. And the benefit here is you can have a more transparent and more interpretable results in this type of research. And then after the coffee break, we have this incorporating unstructured common sense knowledge. So here we use a large knowledge corpus and then use some fact-following techniques that we can do this multi-hop reasoning from the first initial phase and with more and more reasoning steps and get the final answer. And then we also introduce how we can incorporate knowledge for generation tasks. We mainly introduce a benchmark here, the common gen, and we can see there are a lot of interesting work using knowledge incorporation for knowledge augmentation methods for improving the generative common sense reasoning. Okay, so that's all for this part. And I'm happy to take any questions if you have.
Thanks, Bill. I think it's no question on the Zoom chat box. So I'm not sure about the on-site room, but there's no question on the meeting room. So meeting chat.
Yeah. Anyway, please feel free to email me or and you can find the slides online. And if you have any questions, you can always email me about them. Yes, thank you very much. And one host, can take it over.
Yeah, thanks, Yuchen.
Yeah, if anybody can help to turn on the camera in the meeting room, that'd be great, because we did have that before the coffee break. We were able to see the room. Now it's not. Anyway, Wenhao probably can start if you are ready.
Yeah. Okay. Hi everyone. This is Wenhao Yu from University of Notre Dame. So In this section, I will focus on the part of knowledge-augmented methods for natural language generation. And I post some relevant materials in the chat that some materials about knowledge-augmented text generation. Last year, we wrote a survey paper on this topic, and it's just a separate to exam company survey. And also, we post a reading list for knowledge-augmented natural language generation in the GitHub repo, and it cover more than 100 papers. And because in this tutorial, I only cover like 10 papers, and you can find more papers in the GitHub repo. So in this part, we focus on natural language generation. This is a very important topic in natural language processing because text generation is really needed everywhere in our life. For example, in dialogue system, there are many applied in our lives already, like chatbot, ChatGPT, Siri, Alexa, and sometimes when you call the customer service, they all deploy the dialogue system to communicate with people like a human being. And like summarization system, which aims to extract the silent information from the given document. And the machine translation system, which is also a very popular and useful tool that especially for maybe like students studying abroad or when you travel to some countries but don't know the local language. And the paraphrase system, which aims to generate alternative sentence using other words or phrases but expressing the same meaning that maybe like nowadays we use ChatGPT to do this a lot of times, right? And I want to firstly mathematically formulate the natural language generation. First, we have a input X, which is a test, could be a sequence of n tokens. And in real scenarios, it could be a dialogue input or long document for a summarization system. And we wanted to generate also like m tokens in the output sequence Y, which could be a response in dialogue or a summary in the summarization system. And a language generation system is expected to predict the tokens one by one in order to produce the desired output Y. And in each step, the language model generates the token YT is conditioned on the input X and also all previous generated token from Y1 to YT-1. So in order to generate language from the input context, a dominant paradigm, especially in the year of 2020s, with many available pre-trained encoder-decoder models, such as T5, GP3, and many others I listed in the figure from different industry labs. Fine-tuning any one of them on the target dataset is widely used in natural language generation. For example, in the question answering, if given the question like Miami Beach in Florida, brothers which ocean, the goal of the language model is to produce the target answer here, which is the Atlantic Ocean. So we also refer this way as the coast book miner because language model make predictions by only looking up the information in the model parameters. And this is commonly used in many NLP or NLG applications. More concretely, for example, in machine translation, that we directly feed an English sequence into a language model. And if we want to translate to Chinese, and the system use the decoder to translate the English into Chinese. For a scientific summarization system, we feed the entire text of the paper into the model, and the system can output a summary of the paper. If you look at the semantic scholar, you probably can find a TLDR section, which means too long don't read, which is actually the automatic generated summary from the all paper test. So in these examples, in spite of the input and output being different from each other, such as different languages or different document lengths, the content are very similar. Or see globally, they're under the same topic. So we see here in these applications, there are very little semantic gaps between the input and output. However, in many text generation tasks, the input and output sequence are very likely under different semantics, such as the semantic gap between the questions and answer in a question answering or say answer generation task. So think about this question here. Who did Hawaii belong to before 1895? I think this is a pretty difficult question if you don't look at any external materials like Wikipedia or Google. But here now, if I provide you some information that I get from online, from the web. And you can see many relevant sentences appeared in the Wikipedia or Wiktionary or even like structured knowledge bases. And you can combine this knowledge for our like human beings that we can read the passages. And it's pretty easy for us. After reading this, we can know the answers Hawaiian Kindle. So we can see in this type of generation tasks, answer generation, it's very challenging that even our human beings cannot reasonably perform without accessing to an external knowledge basis such as Wikipedia. So as I mentioned, I want to mention why the closed-book model I previously mentioned doesn't work for these tasks when having the semantic gap between the input and output. Firstly, when fine-tuning the language model on the downstream tasks, the language model may forget previous learned knowledge during pre-training, because we know when we ask these Miami questions, it's actually the language model has encountered the relevant materials on the Wikipedia during the pre-training, because BERT or T5 used Wikipedia as the pre-training corpus. But when you fine-tuning on the downstream tasks, and this will lead to the catastrophic forgetting issue. And here's a paper demonstrate the evidence for this phenomenon. And it evaluated on 3 question answering data set. And it classified the questions in the test set as overlap or no overlap. Means if the question overlap means the question in the test set are similar to some questions in the training, though they are different. They're definitely not the same questions. They try to use some similarity metric to evaluate, to measure whether this question is similar to something in the training set. And if you see for the question overlap subset, the accuracy is very high. However, on the no overlap subset, the accuracy is very low, which means the model has remembered many questions it encountered in the training set, but it forgot many things it learned during the pre-training, because in the no overlap set, the knowledge is only from pre-training, but in the fine-tuning, because haven't seen any similar question in the training set. And secondly, the language model make predictions. In closed book model, they make predictions by only looking up the information in the model parameters. So this usually leads to unsatisfied performance and interpretability. And thirdly, the model is trained offline, making the model agnostic to the latest information. For example, if you ask BERT about a question relevant to COVID-19, it probably cannot give you the answer because the model is trained in 2018. And at that time, we don't have COVID-19, this kind of keywords. And finally, they are often expensive to train, especially with recently that the language model are bigger and bigger, like GPT-3 and Palm. They can only be affordable to be trained in some well-funded industry labs. And on the contrary, that I want to introduce is the open book model, which in this tutorial, we also refer to as knowledge-enhanced method. Knowledge-enhanced method makes, in knowledge-enhanced method, knowledge is retrieved based on the input test. And the language model make predictions by reading and reasoning over the retrieved information. So in the figure that you can see, I put the closed book model in the right corner, and you can see closed book model takes the input to the encoder and directly decode the answer. And the open book model first leverage a retriever to get external evidence from any possible resources, just as long as relevant to the input. They could be like structured or unstructured, and different type of the knowledge, and also we can formulate the knowledge from the scope of the knowledge data, such as encyclopedia knowledge or common sense knowledge, introduced by Yuchen a lot of times, and many other exact other knowledge types. So to summarize, closed book model means knowledge is learned to language model parameters. And during fine-tuning, we only feed the input test into language model and make predictions. Examples include BERT or T5 or GPT-3. And the open book models, we also refer as knowledge-enhanced methods. It means knowledge is retrieved based on the input test. And the language model make predictions by reading and reasoning over the retrieved test. Examples include like RAG, FID, which will be covered in this part of tutorial. So before coming to the papers, I want to first summarize from the qualitative side, what is the advantages of open book models? So firstly, the knowledge is not implicitly stored in the model parameters, but is explicitly acquired in a plug-and-play manner, leading to great scalability and interpretability. And secondly, instead of generating from scratch, the paradigm generating tests from some retrieved information, which potentially elevates the difficulty of test generation. So in my part, I will cover mainly about 10 papers in this part, and mainly from three directions. The first direction is how to use retrieval augmented language model for generation. For example, if given a question, the overall pipeline is we want to leverage a RR system to get information from the web, or let's say Google or Wikipedia, or some structured information knowledge like Wikidata or other structured knowledge graphs. And then the pipeline will use the reader model, which is an encoder-decoder model like T5 or even like GPU3, to read the retrieved information to produce the final output. And the second direction is, can we leverage large language model as a knowledge retriever, or say using large language model for information seeking to get some external evidence? The overall pipeline is like we wanted to put the input to a large language model and to get some information from large language model. And the third direction is language model plus memory. So different from the retrieval augmented language model and the large language model, language model plus memory is more specifically designed to a certain task. This memory could be different. In this example, it's like we can use a sports memory, or this can be definitely like movie memory or entity memory, etc. And it's more like a human being thinking process, because we also have a memory to memorize some specific things instead of like memorizing everything like ChatGPT. So the first two papers is a general retrieval augmented NLG model. And the first one is retrieval augmented generation for knowledge intensive NLP tasks. It's a paper published in Europe's 2020. Retrieval augmented generation, also shown as RAG, which is the first retrieval augmented generation work in the literature. And RAG combines a pre-trained retriever, which is a DPR, like DPR style model, introduced by Yichong, I think. And also with a pre-trained sequence-to-sequence model, which is a generator, and fine-tuned end-to-end. So you can see the overall pipeline is when we have some input, we encode the query, and then we use a DPR style retriever to gather documents. And then we combine the input query and documents together into the generator to produce the final answer. And in RAG, there are two variants, most popular variants. The first one is RAG token. Because the scenario is under when we retrieve something, we not only retrieve one, we can retrieve multiple documents. And we wanted to combine these K documents together into the generator to predict the final output. So the token level means the top K documents are retrieved using the retriever, and the generator produces the output sequence probably for each document, and then marginalize each prediction process. And on the contrary, that the sequence model is the generator produces a distribution for the next input, next output token for each document before marginalizing, and repeating the process with following output token. So from the equation, you can see the token level means you summarize the probability of K documents after the generation process. And on the contrary, that the summarization is before the number of tokens in the generation process. So from the experiments, it mainly compares to the traditional retrieval augmented models, but they are not generator. For example, DPR and Realm, they're not a retrieval augmented generation model, but they are language understanding model. They cannot generate something. So that's the reason for some QA dataset, it can be compared as a baseline. But in the generation task, there's no baseline called Realm and DPR because it cannot do generation tasks. So that's the reason RAG is the most fundamental working natural language generation. And then we can see from the QA dataset, we can still see RAGs perform better than Realm on WQ and CT, but the performance is a little bit lower on the trivial QA. But on other generation tasks, because since no previous work on retrieval augmented method, the baseline is still BART. BART is a closed book model because there's no open book models for generation. And we can see REGs perform much better than the closed book model BART. And the second paper is called Leveraging Passive Retrieval with Generative Model for Open Domain QA. It also refers as FID. So the motivation of FID, because REG model suffers from the input sequence length, because in BART is 1024, and also the high computational cost, because when you increase the document length, it is quadratic to the computational cost is quadratic to the sequence length. And the FID process passages independently in the encoder and perform attention over all retrieved passages. So you can see if you retrieve n passages and you use the encoder, separate encoder to encode them, and you get different embedding vectors for each document and passage, if each question and passages combination, and then you concat all the vectors together after encoding. And they use the decoder to attend all the information from this concatenated vector from encoders and to produce the final answer. So this simple but effective method actually increased the performance really much. So as the most competitive baseline REG here, that you can see compared to REG, fusion decoder or say FID improves 10% on average compared to the REG model. And also I want to mention that FID is actually by far the most popular retrieval augmented model owing to its simple architecture and a strong performance. So many of the paper I'm gonna introduce later actually are based on the FID model. So the second part is retrieval augmented model plus larger model such as GPT-3. This topic is recently emerging because like ChatGPT or GPT-3 has powerful reasoning abilities on many natural language generation tasks. And also for the retrieval augmented model, many people in the existing literature also consider whether we can combine the RL system with the larger model together. So the first paper I want to introduce is generate rather than retrieve. Larger model are strong context generators. This is a paper published in iClear 2023. So let's first recall a little bit about the REG, the overall pipeline. Here is when we have an input query or like any input, like dialogue input or summarization input, we have a retriever to retrieve the document from external knowledge bases. And we get the retrieved document, and then we combine the input query with the retrieved document together and put them into the reader model. This reader model could be a T5 model, or FID model, or GPT-3 model to produce the final answer. And what does a closed book model work? For example, if we use GPT-3 as the closed book model, we directly feed the input to the GPT-3 and then to produce the final answer. However, from the existing literature, that we can see retrieval augmented language model, though not using large language model like GPT-3, they still perform better than GPT-3. And on 3 question answering benchmarks, that we can see the performance gap is around 10% to 20%. It's a pretty large gap. And we know that GPT-3 is very powerful, but why GPT-3 still lag behind the retrieval augmented models? The first question we want to ask is, do GPT-3 know the answer? So for example, if we ask a question that who got first Nobel Prize in physics, the GPT-3 will give you the answer, Albert Einstein, which we know this is wrong answer. But if you use another prompt, please provide a background document for the following questions. Who got the first Nobel Prize in physics? So you can see the differences. In this, we have another prompt to generate a background document. And then GPT-3 can generate a document that talking about the first Nobel Prize in physics was awarded in 1901 to Wilhelm in recognition of the service has been rendered by discovering the remarkable race. And this is generated by GPT. And we can see the correct answer is actually contained in the generated document. So the next question is, why do we need to generate document, not answer? So the reason here I want to mention is during the pre-training of large language models such as GPT-3, the document level test is the dominant type of the input and output. So the goal of generating document context for a question can serve as an intermediate step that simulates the language model pre-training. And the second reason is the task of directly generating answers prevents the model from effectively recall knowledge from their memory. Here's an example that we human also do the same. So if I ask you a question like, what was the 10th decimal of pi? So it's really hard question because you probably don't know the answer is 5. But we human, when we think about this question, we probably recall some knowledge in our memory, like pi is 3.14156293535. And we count, okay, the 10th decimal is actually 5. So then we follow this observational intuition that we propose a generate then read pipeline. So compared to the traditional model, like our retrieval augmented model, or directly using GPT-3 for generation, the difference is we first use a GPT-3 to generate a document, and then we use the reader to read the input query and also the generated document to produce the final answer. Or essentially, that our method actually replaces a retriever with GPT-3 generator. So by doing the generate pipeline or generate then read pipeline, we first compare the performance with the baseline GPT under the few shot setting. So compared to the baseline GPT, because GPT doesn't have a retriever, so generate compared to GPT that it has an extra retriever, it's actually instruct GPT. So there's not a traditional retriever. We just like regard GPT as a retriever to recall the knowledge learned during the pre-training process. And the reader will keep the same for the fair comparison. And we can see under the zero shot setting that the generate performs better than the baseline GPT by improving the performance over 60.5%. And also we also do the experiments on the supervised setting. On the supervised setting, the baseline using the retrieval of DPR, which is a pre-trained retrieval model. And our method also used the instruct GPT as the retriever. And for the reader model, both settings use the FID because in the supervised setting, you have the training data to train a retriever. This really performs better than directly using an untrained GPT model as a reader because we want to compare the performance under the up in the SOTA setting. And we can see our model, the generate, improved 0.7% over the SOTA method. So the takeaway here is generate and retrieve beat SOTA under both settings. And there are also other two observations of the generate paper. So the first observation is if you merge the retrieved document with the generated document, you can achieve better performance. So in the figure, we can see the red is combining retrieve and generation. And you can see it's performed better than using either of them. And secondly, is we also showing that this pipeline can work on different large language models, such as OPT and different GPT-3 variants. And it's showing the consistent performance on different QA dataset. And lastly, we also have the experiments on scaling with number of GPT-3 parameters from 100 million to 150 billion parameters. And the green line is the supervised SOTA model, which is the DPR FID model, as I mentioned. And we can see when scaling the number of GPT-3 parameters, and only with the largest GPT-3, it can perform better than retrieval augmented models. It's showing that recalling the knowledge from large model, this capability only presents in large language models. But if you recall the knowledge from smaller language models, it performs really worse than when compared to the retrieval augmented language model. So I want to briefly summarize I show many experiments, but I also want to briefly summarize the advantages and different advantages by using retrieval augmented language model and large language model for information seeking. What are their pros and what their cons? So the firstly is the advantages of retrieval augmented language model is the document corpus is updatable, so new information can be easily pocketed in. And the retrieval augmented language model is really more efficient, and because the retrieval model is small, it doesn't require the model to store all the word knowledge. But on the contrary, that the retrieval augmented language model, because in retrieval, the documents are fixed, they might contain noisy or irrelevant information. And secondly, as I think Yichong introduced DPR, we know that DPR is based on the similarity between the question and document. But in this framework, it only has the shallow interaction between the question and document because the modern retrievers are using the two encoder models, and you calculate the similarity between the encoded embeddings. So we calculate the similarity between two embeddings, only the interaction happens after the encoding process. And another disadvantage is the question and document are from different semantic space. It's really hard to minimize the distance between two different concepts. And on the other side, using large language model to record the knowledge, or say recording the knowledge from large language model, the advantages is large language model has better knowledge storage because it's really larger than 100 billion parameters. And also generation information are more specific to the retrieve information because it's like a customized output for the given query because the document is always depending on the input questions. And the disadvantages is large language models still hallucinate information. That's also existing in every generation models. And the second thing is updating new information into large language model is really hard because training is very expensive and which is often not affordable in academia labs. So the next paper also following this topic is on retrieval augmented black box language model by combining the retrieval model with large language model together. So as I introduced, previous approaches of retrieval augmented language model require to access the internal language model representations. So this is very difficult to apply to very large language models such as GP3. In addition, many language models, large language models, can only be accessed through APIs like OpenAI's models. So internal representation of such language models are not exposed and fine-tuning is not supported. So the thing is, how can we leverage this black box language model and also to train the overall retrieval augmented language model pipeline? So in this paper, Replug introduced a new retrieval augmented language model framework where the language model is viewed as a black box, and the retriever component is added as a tunable plug-and-play module. So this method takes advantages of both retrieval augmented language model and also large language model for information seeking. So to training such a model, it has 3 steps. The first step is we can calculate the retrieval likelihood. For example, if we retrieve 4 documents, and we can know which document is more likely in the retrieval side. And the second step is we calculate the language model likelihood, which means by feeding this retrieved document to the large language model, and you can calculate the probability of the correct answer. So for example, here, the third document is more likely to produce the correct final answer, which means more reliable or more good, more better. And then we wanted to minimize this language model likelihood with this retrieval likelihood because we also want to increase the likelihood of retrieving the D3 document, the third document. So then you can optimize it using a KL divergence. And during the inference time, it's pretty easy that we also using the tuned retriever to gather documents, and then we feed the documents into the language model. And this process can be done during the ensemble process because when you have multiple documents, you can feed each document into the language model, and you calculate the distribution, and then you merge them together. For example, here the example has 3 documents, then you combine the distribution of 3 decoding process when you're generating a token. So for evaluation, that the data on language model evaluation, in this evaluation, which means the lower is the better, and you can see replug has the better performance compared to the baseline, and on MMLU, which is a multitask language understanding benchmark, and also on the open domain QA, that we can see replug performs much better than the baseline models. So to summarize this part, I want to using some questions to summarize this part for takeaways. So the first is, are retrieval augmented language models still needed in GP3 era? So by introducing this paper, we can see the answer is yes. Despite the advances of GP3, that we can see retrieval augmented language models still plays a very important role. They provide the ability to access updated information in real time, and then this retrieved information can serve as input to large language model, such as in the replug model. They're allowing the benefits for both information retrieval and the large language models. And the second question is, can retrieval document be combined with GP3 generated document? The answer is also yes. And we've shown that combining retrieve and generate document can further improve the model performance. And also for other like future direction regarding other topic using large language model and the retrieval augmented language model. So before coming to my answers, I also first asked ChatGPT to give an answer. So I think it's pretty insightful. So I also put it here. And you can see ChatGPT mentioned the future direction is like we can combine the strengths of both generated and retrieval models. I think it's a pretty good direction. And also it mentions like for more interpretable models and to make fair and unbiased decisions. And in addition of that, I also mentioned 3 directions I was thinking. So the first question is, when trust the retriever and when trust the GP3? So in a recent paper that they mentioned, they found using GP3 performed poorly on real entities, significantly left behind by the retrieval augmented language model. So one of the future direction could be for the real entities, we should trust the retrieval more, and on those like frequent entities, we maybe should trust GP3 more. But I don't have an answer, but this could be a future direction to explore when to trust the retriever and when to trust the GP3. And also the second direction is, can we trust GP3? And can we use any external evidence to validate whether these generated outputs are reliable or not reliable? And the third is, can we use structured facts as the condition? Because most of the existing work are retrieving knowledge, such as in the replug. They retrieve unstructured knowledge from the Wikipedia. But the thing is, can we use structured knowledge as the conditions? As we mentioned in the, I think Yuchen mentioned many works using structured knowledge for common sense reasoning, but can we use structured knowledge as condition for large language models? So the next part is knowledge graph augmented NLG models. Is how to use knowledge graph to improve the generation process. The first paper is KGFID, which is a paper published in ASL 2022 on infusing knowledge graph into fusion encoder on open domain question answering. So the motivation here is when you retrieve the passages, the independent assumptions are assumed in the retrieval augmented language model because every document is independent. But actually this is wrong, because when you retrieve a lot of passages, many passages have interrelationship because they are probably mention similar things or they are complementary to each other. And we don't want this passage to be independent when we read the documents. So in KGFID, the general philosophy is it wanted to add a re-ranker to filter document, to filter those documents are not relevant or say not have the interrelationship with each other. So more concretely, that you can see the pipeline could be when you have an input question, and after you get the retrieved document, you don't read it first. You first use a knowledge graph to filter the passages by measuring the interrelationship between the different passages. So here, the core module here is, you can see, use a knowledge graph and using a graph neural network to learn the interrelationship between the documents. And then you can filter some documents are not relevant to this most important or most silent information. And then you feed them into the reader model. So on question answering benchmarks, that you can see KGFID compared to the FID, it improves 1.2% using the 200 million parameter model. And on a larger size reader model, it improves 1.6% on 2 question answering benchmarks. So this paper tells us how to use the knowledge graph to filter the passages are all relevant to each other. Also, this use knowledge graph to help improve the retrieval process. And another paper called Knowledge Graph Enhanced Passage Reader for Open Domain Question Answering, which is on the contrary, like how to use knowledge graph to improve the reading process. So the motivation comes from when you use the reader to read the retrieved passages. We found that like the generated outputs are often incorrect or contradict to the facts. For example, what is the primary language of China? If you retrieve something from Wikipedia, it tells Mandarin Chinese is dominates the public life in the mainland China, and the variety including like Mandarin and Cantonese. But here, the state of the art actually output the answer Cantonese, which is the wrong answer because we know the answer is Mandarin. But the model still make the wrong predictions because the Mandarin and the Cantonese here are both they are pretty near. The position are pretty near with each other, and the model confused about whether Mandarin or Cantonese, which is the correct answer. But the fact is, in China, that we know most of the part people speak Mandarin, and I highlighted only the blue part in Guangdong, they speak Cantonese. So definitely the answer is not Cantonese. Actually, the answer is Mandarin. But we can find some relevant information from the knowledge graph here. That from the Wikidata, we can see in China, there are 1.3 billion people speak Mandarin, which is a count of 95% of Chinese people are speaking Mandarin. So this indicates actually Mandarin is the dominant language in China. So to combining the advantages of knowledge graph, we propose the GRIP method, which combining the knowledge graph into the reading process. So the baseline is we have the question and we have the Wikipedia passages by retrieved through a retrieve system. And then in this framework, we also have a knowledge graph. So to encode it, we have a text encoder, and we also have a graph encoder modeled by a graph neural network. And as I mentioned, we can also retrieve multiple documents and multiple knowledge graphs. They're from the different perspectives. Like we can, on the contrary, that we know 95% of Chinese people speak Mandarin, that we can also know only 17 million people in China speak Cantonese. This only account like 5% of the Chinese people. And we can also know Guangdonghua, also Cantonese, is an instance of Chinese language. And then we use the decoder model to produce the final answer. So here, compared to the state-of-the-art model, which is FID, and we can see GRIP improve 1.1% on 3 question answering data set, and improves like 2.5% on the larger size reader. And for some subset that connected on the knowledge graph within one hop, then we can see the performance more significant. So the takeaway of these 2 papers, and to summarize, the KGFID is the first work of using knowledge graph to improve the passage retrieval via a re-ranking process. And grip is the first work of using knowledge graph. It means the documents are already fixed. No matter what document you retrieved in the first step, the documents are already fixed. And we're just trying to improve the passage reader. And we can see both model improve the performance on question answering. And actually the improvement are pretty similar with each other. But the question here is, can we combining the KG in retrieval and in reader together? Does it lead to better performance? This is also an open question under this area. And the third part I want to introduce is memory-augmented NLG models. And I want to introduce the unified encoder-decoder framework with entity memory. This is a paper published in MLP 2022. So as I mentioned, to firstly recall the closed book and open book models. In closed book model, we directly feed the input into language model and generate the output. And the disadvantages is closed book model lack of the entity knowledge or external knowledge. But on the contrary, the open book model also have the disadvantages because it lack of efficiency, because the retrieve and the read process is very slow compared to the closed book models. So the question here is, can we find a model that have better efficiency than the closed book model, but also the performance is much better than closed book models? The answer is yes. In this paper, we propose a method called EDMAM. So EDMAM, compared to the traditional encoder-decoder model that transformer decoder, EDMAM add another model called entity memory, which is in the middle of the encoder and decoder part that you can see for every input questions. Can we have a memory module to specifically memorize the relevant information during the pre-training process? And then you can fetch the information from the entity memory during encoding and decoding process, and then to predict the final answer. So this memory is pre-trained on the Wikipedia passages and including like different self-supervised tasks to design the pre-training process. And in the generation process, it has three parts. The first thing is freeform generation. And it means we use the entity memory, but we don't specifically to link any entities from the entity memory. But the second is we wanted to, the entity aware decoding is we also link the entity information from the memory. And it divided into static entity linking and dynamic entity linking, which means static entity linking means we first link and then we generate, which is a two-step model. And dynamic is we link the entities on the fly during the decoding process. And here, for the experiments, it mainly depends on two parts, for the question answering and natural language generation. And we can see, compared to the closed book model, the EDMAM performs much better than closed book models. But it still lags behind the open book models, like FID. But here, the advantages of this entity memory model is, you can see the model is much faster than the open book models. And you can see on the trivial QA inference time, you need 40 minutes to get the whole inference on the trivial QA dataset. But if you use the closed book models or entity memory models, you can see the model inference time is within 1 minute. So it's really faster than the closed book models. But you can see the performance lag behind. So in future, we still have to design better these entity memory models to improve the performance if we wanted to compare with the state-of-the-art performance using open book models. So lastly, I want to quick mention some knowledge-augmented NLG models in different applications. So the first one is, can we use knowledge to diversify the question generation, to diversify the content generation? So
sorry to interrupt, Wenhao. Could you wrap up in 5 minutes so I can wrap up the whole tutorial in 5 minutes? We just have 10 minutes left for the whole tutorial, I guess. Thanks a lot.
Mm-hmm. So for the diversifying content, The main idea is, in previous work, we focus on generating the accurate answers. But in many scenarios, we not only need accurate, we also need diverse. For example, in the explanation generation, which in this task is a counterfactual statement. Piano is a kind of sport. We want to generate an explanation that why piano is not a kind of sport. But definitely you have a different explanation ways to explain from different perspectives, such as the usage or effect, or even from the taxonomy. So the thing is, whether we can consider knowledge into helping this diverse generation process, because we not only want to output one answer just. So the thing is, we can introduce the knowledge expert into the model frameworks. It means if the model have different experts, like we have 2 experts here. One expert is maybe good at explaining things from the item usage, and another expert is good at explaining the ways from the taxonomy. And different experts can explain it in the different ways. And can we train the model by explaining making the explanation from different ways? So in this paper, we propose a novel method called MOKGE. It is short for mixture of expert for mixture of knowledge graph expert. So it has 4 steps. The first step is when you have the input, and then we construct a knowledge graph from we extract a subgraph from the knowledge graph, and then we can use a different expert model to extract the different concepts on the knowledge graph. So, for example, the first expert, if you're good at the item usage, and then you got the information from the item usage part. And if another expert is good at the taxonomy, and you get the relevant concept for the taxonomy. And then different expert, because it's extracting different concepts on the knowledge graph, and then you can generate different contents. So in this paper, we evaluate not only on the quality side, but also on the diversity side, that we can see whether this language model can generate 3 different outputs that both satisfy the performance. And we can see for the quality side, higher is better, that we can see the performance is very similar with the state of the art, which means it doesn't sacrifice the quality. But on the diversity side, that you can see the performance is much better compared to the SOTA model by improving the self-blue and the distance by a large margin over the state-of-the-art model. So here is an example that we can see by using the knowledge graph knowledge, the MOKGE can cover some concepts on the knowledge graph, but the baseline actually, it doesn't cover much information on the knowledge graph, but also hallucinate wrong information. And lastly, I want to introduce how to use retrieval augmentation for common sense reasoning. But due to the time limit, I'll skip the most content. But in this part, the general philosophy is, can we use retrieval to help common sense generation? Because in many previous work I mentioned, they are based on the factual evidence retrieval. But this paper also showing that can we use the heterogeneous knowledge as a retrieval corpus to improve the common sense generation process. And the last paper is how to use the retrieval augmentation for multimodal learning, such as in text-to-image generation or image-to-text generation, that you can also retrieve information, such as if you want to generate a text from images, you maybe also want to know what's the name of this place by using a retriever to get external knowledge, that you can better generate a test for maybe like an image captioning tasks. And the pipeline is also very similar, that you have an input image and you can retrieve multimodal knowledge and then put it into the generator to produce the final answer. And you can see by using the retrieved graph, and you can generate better images compared to the baseline, but I'll skip the details here. And to wrap up, in my part, I mainly introduced the different three knowledge enhanced NLG applications, which is first how to retrieve the structured knowledge and how to retrieve the unstructured knowledge, and even like combining the heterogeneous knowledge. And the second direction is how to use the memory network to generate accurate outputs compared to closed book model, but more efficient to the open book models. And the thirdly is, can we combine the retrieval system with large language model by leveraging the advantages of both sides? And finally, I quickly introduce three applications under this topic is how to diversify in the generation, not only consider accuracy, but also consider diversity. And also I include how to improve the generation process for common sense reasoning and multimodal learning. And lastly, I want to also mention, as I introduced at the first, that you can see more information in the survey paper and also to read more relevant papers in the GitHub repo. And thank you very much.
Okay, great. So I'll start sharing my screen. So I don't want to be the one who delay everybody's lunch. So I guess maybe you put up your badge for the lunch, right? So I promise I just use 3 minutes to wrap up the tutorial. I believe that through the last 3 hours, maybe we have convinced you that the NLP models need knowledge. Basically, the knowledge is used to bridge the gap between input and output of the models. And different tasks may have different kind of gap and different size of the gap. And besides the training data or pre-training data, we probably can use some external data as knowledge for improving the models. So you can see there are structured knowledge, unstructured knowledge, or even we may do a really brave idea that is say, we can use large language models as a knowledge source, right? So we talk about quite a few kinds of knowledge augmentation methods, including retrieval augmentation, large language model generation, learning over knowledge graph, pre-trained memory network. So all this can be used to augment the knowledge in the NLP models. There are quite a few future directions. I'll say the first set is like say, knowledge can be further used to address some challenges in the NLP tasks, like hallucination or some long context in the data, and also efficiency, and also lack of explanation from the models. So we can, for example, the last one, we probably can generate explanations along with the decisions. So there's quite a few things you can try. So for the time limit, you can refer to the slides. It's open, so you can take a look at a few future directions as summarized. And another set of direction is to improve the methods of this augmentation. We want to cover knowledge as much as possible, but we'll have knowledge, right? And another thing is we probably have heterogeneity of the knowledge data. So how can we integrate all the things using a unified approach? So how can we find us, right? How this community or the group of force will develop? So we have mentioned the survey a lot. Well, this is the third tutorial we give for this topic. We have given it in EMLP 2021, ACL 2022, and this one is in Wisdom 2023. And we just organized it pretty successfully in AI with our first workshop. So find us with this topic, join us in the workshops in the future. We'll keep organizing the thing in data mining conferences and NLP conferences. So that's all. Enjoy your lunch. Thanks a lot. So we'll be online for questions if anybody has questions, and you can send us emails as well. Thanks.